Hey guys, today we're going to learn a bit about conservation of momentum. So the place where we should probably begin with the idea of conservation of momentum is you need to understand when momentum is or is not going to be conserved. So typically we will say momentum's conserved if there is, say, something like an explosion or a collision and there are no significant outside forces that are acting on the system. All right, now what do we mean by significant outside forces? Well, so for example, if I run across the room and I jump into a wagon and the wagon rolls along with me in it. Okay, I won't actually do this because I'm not a little kid. I might hurt myself and then cry. Anyway, so in that case, we would say there are no significant outside forces acting because probably there's not that much friction that's really going to act during the collision. The largest forces really are the ones that I'm exerting on the wagon and the wagon's exerting on me, and those are internal forces, and friction is negligible compared to those. All right, so in that circumstance, momentum would be conserved. Momentum, however, would not be conserved if I did something like, say, run straight at a wall. The wall is not going to move after I crash into it. So there would be a significant outside force acting. All right, so as long as there's no significant outside forces, momentum's conserved. And if momentum's conserved, then let me introduce you to the only momentum equation you will ever need. Why is it the only momentum equation you'll ever need? The reason it's the only one that you will ever need is because it works for explosions and collisions. It works for every kind of conservation of momentum problem that you're going to see. All right. Now, the way that it's formatted is this. Okay, it's not relating one object to another. That's not what it's doing. Okay. It's relating a moment before the collision to another moment after the collision or explosion, whatever it may happen to be. All right. So this side is for before the whatever explosion or collision, and this side is for after that explosion or collision. All right. So let's apply this to an example real quick. Find example, example I think 2 in your notes packets. For this one we have a cart and another cart. And it says that there's a compressed spring in between them. One cart is a solid 10 kilograms. Oh boy. And the other one is an astonishing 20 kilograms. All right. And then the spring springs. Okay, it's a boing, and the things move apart from each other. And the information you have says that the 10 kilogram cart takes off with a speed of 2 meters per second. All right, if your packet says something different, just roll with it. All right, if it's 2, then so be it. And then there's the spring. All right, and the 20 kilogram cart is moving. Well, okay, let's start with which way is it probably moving. All right, so here's the deal. If momentum's conserved, that means that it's the same before and after. Looking at this, the total momentum must be 0. Got to be 0. Has to be 0 because nothing is moving. All right, so then looking at the other side, the total momentum must actually still be just 0. Well, how can that be, Mr. Erico? They're both moving, right? If you've ever done anything like this before, you know this one's got to be moving in the opposite direction. And so, how can you say there's 0 momentum, Mr. Erico? Because they're both moving. Well, it's still 0 because they're moving in opposite directions. Momentum is a vector. So if this one's moving this way, and that one's moving the other way, their momenta, that's the proper plural for momentum. Their momenta have opposite signs. So if this is, say, positive, this one's negative, and they acquire equal and opposite momenta, so the total is still 0. All right, so it works. Okay, now if I want to plug this into my equation up here to figure out how fast each of them are going, then we can set that up. Actually, everybody go ahead and try and do that. Remember, this goes with before. That side should be really easy to set up. This goes with after. All right, so try and set that up. Pause the video, try and set it up, and then resume when you think you got it. Here's what it looks like. I've written down my one equation. It's the only one you need. Write it down. It's useful for every circumstance, relating to momentum anyway. Okay, now I've done something that may seem a little odd on the left side, and it will become clearer later when we do the next example why I am doing this. But when you have two things that are lumped together, before or after, depending on what you're doing, it often makes sense to write it like this. These two are really, they're like one object because they're initially touching. Later on, when we do collisions, you'll see problems where, say, something sticks to something else, or maybe somebody catches something, right, and then they're rolling along backwards. So those kinds of things, you can lump the two objects together and treat them like one. So often there's going to be an M total instead of having two separate terms. The key idea there being that if they're moving together, they don't have two separate velocities. They have the same velocity because they're moving along together. All right, so both of them have 0 for their velocity. So really just the whole left side is going to be a big fat 0 because there is no momentum initially. All right, over here we've got -20. You could have just said 2 and it would be fine, and then this velocity would come out negative. So kind of whatever there. One of them has to be negative, and I don't care which one. And you don't really need to care which one either unless I specify positive is this way. All right, so that's how I set it up. I set it up with positive being to the right. Okay, whatever. You could do it the opposite way around. All right, so a little bit of math later. Add 20 to both sides. 20 divided by 20. I may have to get out my calculator. No. It's 1. 1 meter per second. All right, now let me point out something here real quick. This should make a whole lot of sense. This one is twice as massive as the other one. So notice it is going half as fast as the other one. All right, I don't know if you've ever done anything like fired a bow and arrow or fired a rifle or something like that. It's very striking if you fire something like a rifle. There's always a recoil velocity, right? If the bullet goes that way super fast, and it is going really fast, like hundreds of meters per second, even though that bullet is really tiny, it has a significant amount of momentum because of how fast it's going. The rifle kicks in the opposite direction. So it's called recoil velocity. It's an explosion problem, right? The bullet and the rifle are initially at rest, and then they explode apart. The velocity of the bullet is hundreds of meters per second. The recoil velocity of the rifle is much, much smaller because it's way more massive. If the rifle is, let's say, 100 times as massive as the bullet, then the recoil velocity would be 1/100th of the bullet. Okay, stands to reason. All right, so there's a ratio there, and it does work out as long as things are starting from rest. All right, now let's take a look at part B. What's the kinetic energy of each cart? All right, pause the video. Go ahead and calculate that for me real quick. So you should get 20 joules and 10 joules. It's interesting to note that the two objects don't get the same amount of kinetic energy. A lot of people, when they're beginning with this, kind of assume, Oh yeah, like stands to reason. Both objects are going to have the same amount of kinetic energy. Of course. If that were true, it would be just as dangerous to be holding the rifle as to be catching the bullet. And we all know that you don't want to be on the bullet end of the gun, right? You want to be holding the rifle if you have that choice, I guess. Okay, whatever. Ignore all the gun analogies. The point is they don't get equal kinetic energies. The lighter one gets more kinetic energy. That's always going to be true, right? Going back to the bullet has way more kinetic energy than the rifle, and that's why you don't die from the recoil velocity. All right. So 20 joules, 10 joules. The next part of this says, where did the energy come from? And hopefully the answer is obvious if you look at this. There's no energy here, no kinetic energy, but then there's suddenly kinetic energy. Where did the energy come from? Must be the spring. The spring is where the energy came from. So that means, part C, how much potential energy must have been stored in the spring? Well, if this one got 20 joules and this one got 10 joules, that means that the elastic potential energy that must have been stored in the spring would be 30. Because that's where all of the energy came from the spring. Conservation of energy. All right. Now, let's flip over to the next one. Next example is also going to be an explosion, but it's laid out a little bit differently. So read the question over, see if you can set it up, and then resume the video. Okay, this should be approximately your diagram for the first part of the question. If you're doing the right one, it's about an astronaut drifting away from the space shuttle. Now, be really careful with signs. Remember, momentum is a vector quantity. So be very careful with signs as you're working this out. Okay, pause. I have set this up here almost correctly. Let's look at the good stuff. First thing is I use the right equation because it's the only one to use. Okay, so the left side is not 0. Don't think about how the wrench is in his hand so it's not moving. No, everything's moving, drifting this way. Oh no! Away from the space shuttle at a velocity of 0.1. So I've done their combined mass, right? Lump them together because they have the same speed of 0.1. All right, now over here on the right side, the wrench has its own velocity. And then the astronaut is drifting, hopefully anyway, back towards the shuttle at 0.1 meters per second. Now, if I set it up exactly like this, I will get the wrong answer. I will get 0.1 here. Well, that's not a throw. That would just be him letting go of the wrench, which will not push him back towards the shuttle. He's got to throw it this way in order to go that way. And maybe that jogs your thinking a little bit. The sign should reflect the direction. This is left. I could call that positive. This is right. I could call that negative. It doesn't matter which one is which. This could be negative. Maybe that makes more sense. He doesn't want to go this way. Let's make this one negative. Negative. All right, now that one can be positive. But you could have done it the other way around. All right, now, if you've done it right from here, here's what it ought to come out to. V1 final is, I believe, 19.9 meters per second. If he throws it that fast, then this will be his final velocity. All right, now try and set up part C now. Pause the video, set up part C, and then we'll talk about part D. I messed up my sign on the previous part. It should have actually been negative 19.9. Okay, fine. That's how fast it needs to go. All right, part C. If all he does is stop, he didn't throw it that fast, he probably threw it slower. If you plug in his final velocity being 0, then it's going to work out that he only threw it at 10, well, I guess negative 10 meters per second, the way we're setting this up. All right, now let's talk about part D. Well, I guess I'm out of time. That's all right. Hope that was helpful.